bubble is in vacuum, there is an ideal diatomic gas inside it, it is being heated slowly, then what will happen? It will start expanding at a great speed. In most of the question in thermodynamics, there is always a relationship given between the thermodynamic variables, like, so 3R by 2 plus 5R by 2, it gives you 4R. So, for this particular process, hello dear students, today we will take up a question based on thermodynamics basically, which also involves a soap bubble. So, this is a simple question but tricky. Once you recognize the trick in the question, it is really a routine question. Let us see how many of you can really recognize that trick. So, here is the question. The question says, a bubble of radius r containing a diatomic ideal gas has the soap film of thickness less than r and is placed in vacuum, which means there is a soap bubble which has a very thin skin, as usually it is with all the soap bubbles. The radius is quite large compared to thickness of the liquid that is forming the soap bubble. So, thickness is too small compared to radius. Now, this soap bubble contains a diatomic gas. The surface tension is sigma, surface tension of the liquid is sigma. Now, the question says, find the formula for molar heat capacity of the gas in the bubble for such a process when the gas is heated slowly so that bubble remains in mechanical equilibrium. Now, by some mechanism, the mechanism has not been specified, but the question says the gas inside the bubble is heated, it is heated very slowly so that bubble is in mechanical equilibrium, which means if you really heat it very fast, then the surface may accelerate, any small segment on the surface may get accelerated. So, that is not there, it is always in mechanical equilibrium. That means any part of the surface is not accelerated, you can always treat it to be at in equilibrium as such. And there is another key word in the question, that the bubble is kept in vacuum. Bubble is in vacuum, there is an ideal diatomic gas inside it, it is being heated slowly and the bubble is in mechanical equilibrium always. What will be molar specific heat capacity? Actually, molar specific heat capacity, it should be specific heat capacity, please. Molar specific heat capacity, ठीक है, molar heat capacity is molar specific heat capacity only. Molar heat capacity means heat capacity for 1 mole, isn't it? So, okay, molar heat capacity of the gas for such a process. So, usually what do we do when we are asked a question to find the specific heat capacity for a certain kind of thermodynamic process? We have a routine procedure that we follow, isn't it? Let us look at the procedure. First thing that is obvious is pressure of the gas is 4 sigma by r. I hope all of you know this. Here the outside pressure is 0 because it is vacuum, right. So, pressure inside the soap bubble is more than the outside pressure by an amount 4 sigma by r, where sigma is the surface tension. I hope all of you know this. So, when the question says that this soap bubble is in mechanical equilibrium, it means this pressure is really this much larger than the outside pressure. If this pressure happens to be far more than this number, then what will happen? It will start expanding at a great speed. So, that is not happening, it is expanding, but it is expanding very slowly. We can always assume that this pressure is 4 sigma by r. If this pressure happens to be larger than 4 sigma by r, then the surface will expand at terrible speed, I mean it will accelerate basically. So, that is not the case, which means always the pressure is 4 sigma by r. Okay, that is understood. Now, the routine process that we follow for finding molar specific heat capacity of a gas in a certain process goes like this. We write the first law of thermodynamics. We assume that certain amount of heat dq is added to this gas. Okay. Because of that, the internal energy of the gas changes by du and work done by the gas is dw. If you supply the heat to this gas, the soap bubble expands very gradually. That is what the question says. Okay, so work is also being done by the gas because it is expanding, volume is changing. So dq is du plus dw. Now dq, the heat supplied can be written as nc dt, where dt is a small change in temperature of this gas, n is number of moles of this gas present inside this soap bubble, and c is the molar specific heat capacity for this particular process. This is the definition of molar heat capacity, isn't it? If I supply a heat dq and temperature changes by dt, then definition of c is dq by n dt. That means rate of basically the molar heat capacity simply means that how much heat is required to change the temperature of 1 mole of a given gas by unit amount, by 1 degree Celsius. So dq heat is required to change the temperature by dt. dq by dt is amount of heat required to change the temperature by 1 unit, and for 1 mole it will be 1 upon n dq by dt. That is how you define molar specific heat capacity. And everybody knows that for any kind of process associated with an ideal gas, the change in internal energy is always ncv delta dt. So I have written du as ncv dt, and if the pressure, instantaneous pressure is p and small change in volume is dv, then work done is p dv. So this is the standard thing, isn't it? Now what we do in any question, we try to express this in terms of change in temperature. If dt cancels out, you get the value of c for a specific process. So the most critical thing is to manipulate this term to express it in terms of dt, change in temperature, and there is a fix right now. In most of the question in thermodynamics, there is always a relationship given between the thermodynamic variables. Like if I say that gas is executing a process where PV square is constant. Suppose I say that gas is undergoing a process where PV square is equal to constant. If any such equation is given, then we, along with this equation, we use ideal gas equation, and we are able to somehow manipulate and express this in terms of dt, and that gives the answer to our question. But the serious problem here is there is no such relationship given here. Can you see any such relationship given in this particular question? Can you? वीडियो पॉज करके सोचो, 2 मिनट, 3 मिनट, 4 मिनट, 5 मिनट तक सोचो एक बार. Can you see this kind of relationship given in this question? Please pause the video. Yes, there is one such relationship given here, isn't it? This is the relationship. Can you see that? Can you see that? What is this? This is basically P into R is a constant. The surface tension is a constant. So P is pressure of this gas, R is the radius of this spherical enclosure, spherical bubble. So pressure into radius is constant. So actually pressure और volume के बीच का relation दिया है, isn't it? R cube is proportional to volume. So if you cube this, just put cube on both the sides, what do you get? What do you get? P cube, P to the power 3 into volume V is a constant. So that is the relationship. That is the relationship. This is the relationship that is given actually. If you just take cube of this expression, then R cube is some volume into some constant, volume by some constant, or volume into some constant. So P cube into V is a constant. That is the relationship that is given here. So now the question becomes extremely easy. I guess many of you will now be able to solve this question very easily. अभी भी कर सकते हो तो कर लो. मैं जल्दी से बहुत जल्दी से इस क्वेश्चन का सॉल्यूशन यहाँ पे आपको दिखा देता हूँ. So now the next step is I have divided this by dt and dt basically, and this becomes C is equal to Cv plus P dV by n dt. Just simple manipulation. Now my necessary step is going to be find dV by dt by some way, and now I have got this relationship, so it is very easy. Now use this equation along with Pv is equal to nRT because it is an ideal gas. So using this equation along with Pv is equal to nRT, you will be able to prove that T cube V minus 2 is a constant. It is very easy. I mean, you just need to eliminate P. Pv is equal to nRT. So in place of P, you can write nRT by V, uska cube. So you can easily see that you will get an expression of this kind. if you separate all the constants on one side. Now you can take logarithm of this equation and differentiate, because I want to get dV by dt. So just take logarithm 3 log t minus 2 log v is equal to constant and differentiate it with respect to t. If you do that, you will get dV by dt is equal to 3v by 2t, 3v by 2t. So just substitute dV by dt is equal to 3v by 2t here. Here is the substitution. The value of Cv for diatomic gas is 5R by 2, and in place of dV by dt I have written 3v by 2t. Now this is simply 3 by 2 of PV by NT. Now PV is always equal to nRT. So if you write in place of PV nRT, if you put nRT, n will cancel out, t will cancel out, and you will be left with 3R by 2. So 3R by 2 plus 5R by 2, it gives you 4R. So for this particular process, the specific heat capacity is 4R. आप में से बहुत सारे लोग याद करके रखे होंगे कि ये एक पॉलीट्रॉपिक प्रोसेस है और ऐसे पॉलीट्रॉपिक प्रोसेस के लिए स्पेसिफिक हीट कैपेसिटी का ये फॉर्मूला होता है. यस, you can use that formula directly to get the value of specific heat capacity, but the critical thing in this question was to obtain this expression. This is the relationship that you were supposed to find. I hope you have understood this. See you in the next video with a new question, a new concept. Thank you.